Good evening. We welcome you back to the next session of the first day enterprise. We are fortunate to have with us Professor Deshpande with us. He has been with us in our previous workshop too, and many of you who are attending today know him very well. Desh is with Ayuka and IITK right now. He is a brilliant radio astronomer, a Bhatnagar Award winner, and he's been kind enough to interact with the students very patiently, and they've done a wonderful job with him. So he'll be talking to us this time on the 4Cs: convolution, correlation, coherence, and calibration. In general as well as in astronomy. Okay, over to you, Desh.
3 sessions. So all 3 afternoons, you will be able to hear him from 4:15 to 5:15 on all 3 afternoons, Friday, Saturday, Sunday. Yeah.
So over to you, Desh. Thank you.
Thanks, Najam and Priya, for this opportunity to share random thoughts on these aspects which we encounter often enough. I would like to admit and apologize right in the beginning for what is going to be the most incoherent rendering on these topics. We will see how many of these aspects that we hear names about and even perform these operations from time to time are all related and form important pillars in the kind of astronomy pursuits we take up. And so while we do this, since it's going to be more informal than usual, I would request you to interrupt me anytime and ask questions, or ask me to clarify things if I have not said them right, or correct me when you notice that I have faltered somewhere. So with this, let me begin. We are going to look at some of the pictures first, just to familiarize ourselves with what we are talking about and how it's closely related to what we already have come across. So let me start with convolution, which is generally in equations and so on, or as a symbol, it's indicated with this star sign between functions, implying that's the convolution of the two things on either side of it. And in general, it's a linear superposition of weighted and shifted ingredients that we have. And if you like, the weights and shifts are decided by one of the functions, and the ingredients can be the other function, and the roles can reverse seamlessly. So this is how a typical linear system would, sorry for this references to what might appear like engineering aspect, but it can be any black box, which is a linear system to which we give any input, and based on the property or response of this box, we will get the output, which will scale appropriately with the input. The important thing of linear systems is the property of the system itself, which is indicated here, for example, by the symbol h of t. It could be h of x or h of any multidimensional description. Does not depend on what is the input. And that's the hallmark of a linear system. It will do the needful regardless of what is the who's asking the question. It will simply respond to the question in a way that it always does. So, so it's an unbiased thing. It doesn't look at the input to decide its behavior. What will be the output, of course, is decided by what is the input, and it will appropriately answer the question that is asked to the system. So here, for example, it's a very familiar example. On the left top, you will see an image of the sky made with a telescope, which has some response function. And you will find that it has responded to the input associated with amount of light from every star in the fairest possible way. It has responded to it in the same way everywhere. Of course, because of the brightness being different for different points, you may or may not see the response in its entirety, which in this particular case is, streaks along this plus, along the plus sign, and a bright blob at the center and a slightly diffuse blob around it. And this response is something that any single point in the sky will receive from an observing setup like a telescope. And so you will find that what has happened here is a convolution of the brightness distribution in the sky with the response of the telescope. The other familiar example that you would have come across, less mathematical, is when you look at an image, an arbitrary image, and you blur it. Some of these facilities might be available in your image processing softwares on your computer. So if you smudge it with something which, for example, is shown here, it has got this weightage given to pixels on either side of the pixel that you center at, and the combined contribution from all the pixels around it is what is output in this new pixel at the output. And you will find that if it's combining information from surrounding pixels, you would lose the sharpness that you had in the image. For example, in this, I hope you can see my cursor. So what is in this image is smudged or blurred in this. What has happened is we have convolved this image with a function, which is this two-dimensional kernel, you might call it, or just another function, which might have certain shape, and so you will relate these numbers to the kind of weights that I'm talking about, and the shifts are like taking contribution from something which is not at that location but shifted, but it's now contributing to this pixel at output. So you will find that what we have done is we have taken shifted and weighted contributions from all these pixels onto the pixel that we are querying about as an output of, which is a result of what we immediately appreciate as a convolution. You can also imagine convolutions when, or represent certain things as convolutions when, for example, you encounter a pattern like this. Let's say a shape of a house or house itself with repeated intervals or at intervals of whatever specified measures. You can imagine them to be one function to be a set of delta functions at the locations of at the centers of these patterns, and that set of delta functions are convolved with a pattern which is what is seen to be repeating. And so you'll find you're putting a replica of this pattern at every location of the delta function. Of course, the pattern here need not be confined and small compared to the separation of these delta functions. It could be much wider, in which case you can imagine that these patterns will overlap, and what you will get will be the result, which may not look as neat as it looks presently, but it's still a convolution of a set of delta functions with the pattern at hand. Similarly here, one in more technical context, you can see a repeating sequence, like in the case of pulsars. Of course, pulsars don't give rectangular pulses, but whatever shape that might be there, which is repeating at intervals of the rotational period of the pulsar, can be thought of as convolution of a set of delta functions with the pulse pattern described separately. And you will find when you convolve the two, you will put replicas of every function at this location of the delta functions. I'm emphasizing this purposely, as we will see, this might be a more convenient way of viewing convolution, which is often described mathematically in a way that doesn't bring out the simplicity of this operation. Okay, I'm going to first sort of sensitize you on familiar aspects of all these four C's. So let me go to correlations. We are of course going to go into great details on this later on, and the context in which we use these in general and in astronomy context. So correlations are familiar to you. You would have made scatter plots of data sets available in in two entities, for example, plotted one against the other for every discrete measurement or information that you have, and you would have tried to see the behavior, and naturally you would be interested in seeing if there is any relation between one parameter with the other. And that is assessed by formally seeing or even computing cross correlation or correlation. And that is done routinely by either plotting them visually and examining them visually, or computing things in the computer by some number crunching. So here are some examples of strong positive correlation when two entities have some relation with each other. You will see that when one of them is high, the other one is also high, and one of them is low, the other one is low. And so this is a positive correlation. It might be just a hint of some correlation, but may not be very strong, in which case you will see large scatter of points about the line describing the mean trend. In cases where there's no correlation, there won't be any particular preference of this trend. The correlation need not be always positive. You can have correlatedness, but it might imply that where is my cursor? Yeah. So when one of the entities is high, you might find the other one is low or high in magnitude, but might have an opposite sign, in which case you will get strong negative correlation. That correlation may or may not be very strong in certain cases, and you might see more scatter around the mean trend, and so on and so forth. So this is something that we have done many times. You can quantify this in terms of formal coefficients, which take into account or ignore the aspects of exact nature of the entity, its spread, and units, and so on and so forth, and it gives you a purer measure of a more universal measure of the relation between two parameters at hand. You can also see this in terms of if these points are systematically available in a form that you can represent them as a curve, then you will find that as a function of some other parameter, both these entities which were typically plotted here could be a function of a common parameter on which you can make this plot and see whether there is similarity. And that similarity can be assessed by actually seeing how's the match between the patterns that you see. And that can be seen by, even if the patterns are staggered, you can slide them over each other, and like we would like to see if two patterns are available on the drawn on a piece of paper. We have two such papers. We often put them on top of each other and view against some bright light to see if the traces match, and we can even slide them arbitrarily to see if they look alike after sliding them together. So one can even compute these as a function of the slide amount, and or can be called relative shifts, and see whether there is any match. So correlations are used in assessing similarity. Convolutions are, although their formal description, mathematical description, looks very similar to the correlation integrals and so on, are entirely different entities. Correlations can happen in nature, convolutions can happen in nature and in systems seamlessly. Correlations have to be performed. You can see that you can even take an arbitrary, I gave you an example of a one-dimensional entity here. You can even have a 2D description of something here, an image and a slightly offset image. Otherwise, they are identical or may not be identical. But you can compute the correlation between them by actually sliding them over each other each time, assessing what is the commonality between them, and then plotting the measure of that commonality as a function of the shifts. And you will find that you will get a bright spot here indicating that this is the relative shift at which the match is best. But it also doesn't, the match doesn't drop suddenly because of the scale of the patterns here. You will find a diffuse glow of high degree of match continuing for some amount of shifts. But certainly the peak indicates the right amount of shift at which the matching is maximum. Coherence is a most subtle entity, and one has to be most careful about assessing coherence, particularly before one makes any statement about lack of coherence. When the coherence is there, of course, it's obvious, and you don't make a mistake in asserting that there is coherence. But when you encounter a situation where there is hidden coherence, although it doesn't appear like there is at the outset, that is when you need to do several things to ensure that you have not missed to recognize the hidden coherence. Coherence has two aspects. One is the internal coherence of a process. If I'm describing something, whether, for example, if my talk itself, without, any interface between you and me, whether I am speaking coherently or not would be my property. And whether we, in a discussion, whether we are doing things together in a manner that have a lot of similarity and are in sync with each other or not will be assessed by mutual coherence. So, for example, internal coherence, there is a very good example of a light from a LED or flashlight, where the light source is some arbitrary source, as against the laser, which gives you light in a very coherent state, and this has got high internal coherence. Similar things can be done where such a source, what might appear like otherwise incoherent source, can be made coherent by appropriate filtering, first through a spatial filter, by allowing light only through a small pinhole, and then which will have a well-defined wavefront. Wavefront is nothing but equiphase surface. And then it might still have contribution for a large number of frequencies or colors, which you can filter out via wavelength filter and have a much more pure state of the light, which will be highly coherent. So this will have a large amount of both spatial and temporal coherence. You will have situations which are encountered routinely, where you have a point source in this, either in the sky or on a tabletop, and the wavefront emanating from it would be can be sampled at 2 points by 2 observers. And now when we assess the level of similarity between what P1 and P2 receives, we are assessing mutual coherence. Of course, that level of coherence, of course, is not very high. When you have an extended source, the wavefronts are not as nicely defined as they are here. But we will come to this, and that forms basis of some of the finest techniques we have in measurements in astronomy. Of course, while assessing the coherence, as I said, we would be leaning on things like correlation. Coherence is assessed by using correlations, where if we were to formally correlate the picture of this apple and that apple, which is I have produced by simply scaling one from the other, you will find that the correlation is not great, and you might dismiss this as lack of coherence. Whereas that there is almost point-to-point relation between what is happening here in the picture and what is happening in the bigger picture. And so it doesn't require any guessing that to say that there is high degree of coherence, although the apparent formal correlation might show a smaller value than you would have expected. So this is the care one needs to take, that even if in this picture, for example, if you have the apple placed at a certain location, different from the relative location in the picture of this apple, even if they were of the same size, you would find that the correlation is not very high if done blindly, if the comparison were to be done blindly. And so you will find that lots of shifts, rigid shifts, translations, scalings, and even rotations need to be allowed for before one dismisses some comparison as indicating lack of coherence. This is also true in the context where you might have a coherent source, but giving light in because of relative motions of the observers. The observers might see light red-shifted or blue-shifted, and if you do a blind comparison, they may not appear like there is any similarity between them, but knowing all the physical processes that might be at work and allowing for them, if you do the comparison, you might find high degree of mutual coherence. This is another aspect that we will see how it. So we have seen that coherence is something that is to be assessed with using a tool which is correlation, which is a measure of similarity. But while doing that, we need to be careful. And so we will see many examples of all this as we go along. calibration is at the heart of the usefulness of any measurement you do before it can be translated into the real information we are after. After all, any measurement that we do requires tools to or ways of making those measurements, and each one of them has its own idiosyncrasies or characteristics which leave an imprint on the measurement, both either in terms of the limitations or the blurring or the uncertainties, which might be systematic or random. We can't do much about the random uncertainties, but the systematic uncertainties we need to take into account. So essentially, it's trying to translate or trace back any measurement to the original information that we were after. And this involves understanding of the process that we have used, the tools or instruments that we would have used, their characteristics, their imprints, measuring them themselves as accurately as we can, which sometimes they might be changing as a function of time or might depend on other parameters. Taking all that into account, we need to really distill out from what we see as an apparent measurement to what the information we were after. So it might be, from a blurred image, we want to see actually things that's in detail at the fine level that the information really exists. We might want to correct for the spectral or temporal imprints that our instrument has left on the data, measure them correctly, and after having corrected them, we get a measure of something that we are after. You can basically all the processes that happen while treating the input and bringing it to the level that we can measure things will involve some kind of filtering, some kind of processing which modifies certain pieces of information or combines certain pieces of information that we need to disentangle and bring about the original information. And so many times convolutions happen naturally, and we need to deconvolve. For example, even in the image that you had, the calibration there of the set of stars that you observed with the telescope, which had these streaks and the response of the telescope around each star location. You need to remove that effect. You need to measure it in its own way properly, or at least model it properly, and then remove them. So that might involve some deconvolution and so on and so forth. You might need to remove contributions which are essentially additive and multiplicative on the way, and each one of them will require either a clear knowledge of it or measurements to assess what that effect is. Okay. Now, in all these, we will be using something which I just flashed briefly. The Fourier description of most of the things that we encounter, either as one-dimensional entities or two-dimensional entities or multi-dimensional entities, either in form of signals or images or things like that. So we will require essential familiarity with the Fourier domain descriptions of several things, because many of these issues relating to convolution, correlation have very elegant counterparts in their respective Fourier domains. And so I'm going to spend rest of the time taking you through the Fourier transforms, even though many of you might be already familiar with them, so my apologies. Or maybe at this stage I ask students to or listeners to indicate to me whether they are already familiar and one can avoid this description.
You all can add on the chat box if you all want, whether you would like sir to do that or.
Yeah.
Yeah. Hello, everyone. So there's already a question.
Yeah, right.
Should I read it out to you or can you see it?
Yeah, I can also see it while I post this question. Okay. 1 minute. Okay, his question is in two parts. In statistics, how is the correlation related to the result? Is that relationship quantitative or qualitative? Yeah, so in it can be very quantitative, and in statistics, particularly dealing with uncertainties of various kind, owing to the certain level of randomness and the limitedness of the statistics, you will have uncertainties also associated with the quantitative measure. So while correlations are good to look at qualitatively in terms of these plots that I showed you, formal seriousness of the level of correlatedness is to be assessed quantitatively and in the light of level of confidence you have in saying that something appears to be related to something. So is tied up with the uncertainty you associate with it and the confidence level you associate with the claim. Okay. Second is, I might be wrong, but you mentioned that correlations don't occur naturally. Why? You can make correlations appear naturally by designing something, but convolutions are the natural phenomena where you have any linear system, you poke it and it will respond. This is even related to you and me. You asked this question and I responded based on as a system. So what has happened is, my output has actually been a convolution of your question and my understanding in resulting in the answer.
What's the name of this person? I can't see a name. Who is this?
Satyaki Goswami.
Okay.
He had asked this question.
Okay. Okay, so yeah. So the next thing was, should sir proceed with Fourier transform intro or should we go ahead with Fourier transform, please? Go ahead, sir. Very nice talk.
Okay, so it looks like at least two people have responded who have said yes, unless others have objections. So maybe somebody who doesn't want that to happen can say it. That will presume that the rest of the others are okay with it.
I think yes, go ahead. They say, go ahead.
All right. Okay, so I will go ahead. So this will might be a repetition of several things that you might have already been familiar with. But I will try to go over it as quickly as I can, so that we have the foundation of it, and we will be able to walk from one domain to the other domain rather easily while we describe these four C's. That's the basic idea. Okay, so we will be refreshing our already gained understanding of Fourier transforms. As you know, among the various great things that Fourier did, these transforms named after him have enriched and transformed many academic lives. Will continue to. So the basic idea is very simple, which you are already familiar with. Any given function, we will see what the property of the given function should be for it to be, describable or viewed like the way I'm going to describe. But a given function, when can be viewed as a linear superposition of a large number of sinusoids of various periods of oscillation, each scaled and phase shifted appropriately so as to collectively describe the function at hand. So this is the basic idea, right? You give me any pattern, I then imagine, and that word imagine is not so arbitrary or doesn't depend on my creativity. There are formal ways of actually getting the associated descriptions very easily, which we'll come to. But for qualitative description, it suffices to say, take a pattern and imagine that to be made of superposition of large number of sinusoids of different periods and different amplitudes and different phase shifts with respect to some fiducial point. And then if it can produce this function, we can use this description of various sinusoids, arrange them in increasing order of their frequency, and note down their amplitudes and phases that we use as a contribution to this grand superposition. And the description itself is the Fourier transform of this pattern, right? So this is what Fourier transforms are all about. Here, as we will come to, we have the functions that we have used are specific. They're not some arbitrary functions. They are sinusoids, and these are called basis functions. We are going to use only these as basis functions. That means everything that we will try to realize will be a combination of only these sinusoids. When I say sinusoids, cosines and sines are indistinguishable. They can be written as one, or in general as a combination of the two in description in a complex plane, where you can define the amplitude and phase of the phasor which is oscillating at a given period of the sinusoid. So these are similar to many linear transforms, and as I said, the basis functions here are sinusoids. The important thing to realize is these are very strictly linear transforms. That means the coefficients which appear in front of these functions are not, they are simple constants. Those coefficients times the sinusoid to the power unity. Okay, it's not higher power contribution from each one of the sinusoids. So it's a linear combination of a large number of sinusoids with respective coefficients. And it's the set of coefficients arranged in a certain form that describe the Fourier transform. So you will find that each one of them will be scaled and phase shifted. And the idea is to collectively patch the function. So sometimes we will require some sinusoids, sometimes we may not require certain sinusoids. And so all that will be taken care of appropriately by the scales being 0 or non-zero, or being whatever they are appropriate in the description of the contributions from various sinusoids. So the Okay, so I think this I've already said. The important other aspect about Fourier transform is there is no change of information content. When we go from one domain to the other, whether we describe them in the form that the function was available, or describe them now in the set of sinusoids whose amplitudes and phases are defined and given in certain order for convenience, the amount of information has not changed. Whether we give this or that, there is no loss of information. It's neither enhanced nor reduced. So it's like an accurate translation across languages, and the reverse translation should recover the original message. So if I give you a set of sinusoids with their amplitudes and phases defined, you would be able to superimpose them and get back the original pattern, even if that pattern, how it's going to look like, may not be instantly apparent from the pieces of information I have given you, till you superpose them. So in this way of the reversibility of this operation, one needs to ensure that there is uniqueness in the representation of the complex factors as a function of frequency, which requires that the basis functions that we're going to use, that each one of these sinusoids, are not having anything in common with each other. They are mutually orthogonal. Another way of stating them is, if you were to represent them in multidimensional space, which are basically the samples in time, let's say, of each one of these sinusoids, or along x, along which they are described, the vector that you will get has a dot product 0 with any other sinusoid. Or formally, when you compute the cross correlation between two such sinusoids, the net result will be 0, of course, as viewed from range which goes from -infinity to +infinity. Over small range, it might appear to have correlation, but it's not really a real correlation. So what you want is each one of those sinusoids to be orthogonal, and for the net correlation to be 0, you need basically another condition which is not stated explicitly, that any one sinusoid should not be producible by any combination of all other sinusoids, right? You might say that one sinusoid doesn't have anything common with another sinusoid, but even any conspiracy of all other sinusoids should not be able to produce a given sinusoid. And so that level of independence is at the heart of being able to use these as basis functions to ensure uniqueness of the description. That means it's like the salt. The salt test cannot be produced by any combination of other tests that we might have. And so they are like the basis functions in the context of tests. So when we want to describe the taste of a particular dish, we might say, okay, a little bit of this, little bit of that, and so on and so forth. And we're describing a spectrum of tastes, much like the description of the spectrum context that we have here. The important thing there is that it's a unique description of the measures in which different tastes contribute, and no one taste can be produced by any other combination of other tastes, linear combination of other tastes. Okay, so what is the other condition that we require? That while we want them to be independent of each other, we also want the set to be self-sufficient as a collection of functions to be able to describe any function. Now, when I say any function, within certain limitations And in general, very loosely stated, you can say any given finite function to be described as linear superposition of these basis functions, you need the set to be comprehensive enough. So essentially what you want is the basis functions should be mutually exclusive. They should be exclusive of each other, and collectively they should be exhaustive of all the possibilities. So with this, and this is true of any other transforms that you might want to consider with different basic functions, and for them to possess this property of uniqueness and the orthogonality, you will require these qualities. Fortunately, sinusoids as basis functions satisfy both these requirements. The formal definitions of it, of course, are very familiar to you. We can compute formally the Fourier transform capital F of S, which is a conjugate coordinate with some x that we have chosen, in which a function small f is described. We want to compute its Fourier transform. We would find that we can extract the information associated with the particular sinusoid, which is contributing in this grand sum, which describes the f of x, by simply multiplying it by e to the power minus xs minus I being the root of -1. Some people would like to call it j, and so on and so forth. So this is the transform, and you can, of course, convert that information back in terms of superposition. So these become the coefficients, and the sinusoids are described by this e to the power ix times s, and you will find the s defines sort of the period, the frequency, and the function is described over the range of x. And for a given x, if you want to know what the contribution from that particular sinusoid is, you need to know its amplitude and phase, and the sinusoidal pattern itself, what it will be contributing at the point x. And if you sum over all this, you will get the function back. So here you're doing the filtering operation. You're trying to extract the information from this grand superposition by multiplying by something which is the pattern itself or a conjugate of it. And you can see that if this was made of a summation of a large number of sinusoids, you will find that multiplying it by a particular sinusoid leaves you only one non-zero entity from this summation, because all other terms in the summation would not relate well with the pattern that we are looking at. Everything else, when multiplied by this pattern, would go to 0 on integration, and the only pattern which would give you non-zero contribution is exactly oscillating at the same frequency of the probe. So that's the basis for extracting these patterns, and the other way you can, so people call it Fourier analysis and Fourier synthesis based on the way you view it. But they are interchangeable, the meanings are interchangeable, and so there is no particular importance you need to give to it, because the other way description is identical in terms of spirit. So you will find that the conditions formally stated, although they can be discussed in greater detail, I'm just taking it from one of the available nice descriptions I found on the web, from which I've extracted this conditions. If the integral of modulus of f of x exists, integrated over from, that means it's a finite integral of the modulus, and any discontinuities in the f of x are also finite. In which case one can describe these functions through the Fourier descriptions. The appeals of Fourier transforms are many, and some of them we're going to use explicitly while understanding or even computing convolutions and correlations and even visualizing them. So, and as you know, these are very important descriptions connecting pairs of aspects in optics, descriptions in one domain and in the other domain can be connected very easily, and they appear very explicitly in the in optics. For example, the lens that we use routinely is actually a Fourier transform, and one can appreciate that after seeing what actually the lens does. So there are several subtle and direct aspects in which we find Fourier description very empowering, and of course more specifically relevant to astronomy, instrumentation, signal processing. We can make certain computations very efficient, convolutions and correlations, also integrations and differentiations, which we don't encounter so routinely in astronomy, but in mathematics you will find there is huge convenience provided by the Fourier domain counterparts of these operations. It also provides a facility when we said information does not change across these domains. Many times it might be difficult to measure certain information of interest in one of the domains just because of the the sheer difficulty in making such measurements or having appropriate instruments to do those measurements. So one can say, okay, the same information can be measured in its Fourier domain if it's possible, and then it's a trivial translation to this domain. Of course, in doing that, lots of subtle and direct effects have to be taken into account, both in terms of completeness of these measurements and any other effects that might trickle in. But it certainly provides an opportunity to opt for a feasible domain in which measurements can be done. There are also fantastic other advantages which are more qualitative and which are more exciting sometimes in gaining insights that both visually and in terms of actually exact operations that might be happening or the processes underlying certain phenomena. By viewing these functions in one of or more of either of the domains, we can see some of the influencing effects, how they can be captured much more easily and can be visualized much more easily. We can, on top of it, see many of the phenomena might have certain compactness and elegance in the description that they might present in one of the domains. That elegance and compactness in particular would be or should be viewed as a measure of or appreciation of the level of coherence that it might possess. And so many times it's profitable and empowering to have descriptions in both the domains. It's not always meaningful to have one description and feeling compelled to look at the other description and feeling compelled to use it. After all, you would like to go to a domain in which the elegance and compactness might exist and certain subtle messages can be apparent. There you don't have to feel forced to take a Fourier transform of something as soon as you have it in hand. You might already have a very elegant and beautiful description in the domain in which you are looking at, and the other domain description may or may not be as useful. So with that message, let's look at some of the properties. I will not spend too much time, but you can see the as any function, any function that can be described as proposition of odd and even parts, which can be easily computed by looking at the function on either side of the origin. You can see what the Fourier transforms would be, and they will have certain properties. For example, real and even functions will have Fourier transforms which are real and even. Real and odd functions will have Fourier transforms which are imaginary and odd. The one that we encounter more routinely is real and asymmetric function, which, like the sky brightness distribution, we will find that it has Fourier description which is complex, and but has certain symmetry properties which are called the Hermitian symmetry, where the contribution on either side of the origin diametrically opposite will be complex conjugate of each other, which means the real parts are equal and the imaginary parts have opposite sign. So real parts of the description in the Fourier domain will be symmetric, and imaginary part description will be antisymmetric. I will leave you to look at these at leisure. These are useful, but not essential right now to our proceeding with them. So that you can visualize these and see how the Fourier transforms will also carry certain properties based on the function being Fourier transform. So in general, I've been saying that we consider superposition of large number of sinusoids. Here is how the function might develop as we keep on adding sinusoids with different frequencies, as we begin to differ from looks of any one of them individually, and it might acquire a completely different looking property, although each one of them has contributed to this description in certain measure. For example, the dotted function, which is a combination of these two sinusoids, sine wave 1 and sine wave 2, begins to have less and less similarity with any one individual function, but it still contains uniquely the imprint of each one of those sinusoids, which can be separated out without any ambiguity when we need it. So also you will see that what were highly periodic functions when superposed together, with, which had different periodicities, now the net function will not appear to be periodic anymore, and that's not a big surprise, unless there is a certain phase relationship between and the frequency relationship between the sinusoids that you superpose. And one such example is that of us, there are many examples. I've just chosen here of a square wave where sinusoids of frequencies which are harmonically related are superposed on each other with certain phase relationship. And you will find that superposition leads to this sharp pattern, which is at the same frequency of this fundamental contribution. But the sharpness is something that was not there in any one of those smooth curves that we added together. All right, so you can go on and on, but let's go to very general descriptions of functions that we encounter, whose Fourier descriptions, having them handy, is very useful, so that we can visualize them readily when we see a function, or when we see a function, we can visualize that in components or, as combinations of certain kind in one domain, and we can immediately visualize knowing their counterparts in respective counterparts in the Fourier domain. We can visualize the Fourier domain description without having to compute it explicitly. So one of the famous functions, the Gaussian, has a Fourier transform, which is another Gaussian, where the widths are related inversely to each other. For example, a narrow Gaussian in one domain is a broad Gaussian in the other domain, and so forth. This is one of the properties that we will highlight as we go along, the inverse relationship. Remember that in the arguments that we had in the Fourier integrals of the exponent, we had combination of the two coordinates as a product. And that means you can scale any one of them, and that can be that will have effect of scaling the other entity in the opposite direction. Okay, there are some questions which I would I'll probably come to that later. Get distracted right now in the middle of this description. So let me complete that. So Gaussian has a Fourier transform as a Gaussian. If we have a rectangular function, it has a Fourier transform which is sinc sin x by x, and vice versa. So wherever we are denoting these pairs, please be reassured that whatever is on the left side has a Fourier transform which is on the right side, and vice versa. So you will find that you can have a triangular function whose Fourier transform is sinc square, and we will see how that relates to having known the Fourier transform of a rectangular function, and how rectangular function is related to the triangular function, which would have allowed us to compute the Fourier transform of a triangular function directly by knowing this original relation. Another very important function is a simple delta function at the origin in one domain, which has a Fourier transform which is constant as a function of coordinate in the other domain. So much the same way, any constant, any function which is constant as in one domain has a Fourier transform, which is a delta function in the other domain at the origin. A sinusoid, a cosinusoid, for example, has a Fourier transform which is pair of delta functions with equal phase and amplitude. A sinusoid has a Fourier transform which is similar to delta functions at the same locations, but having phase shift with respect to each other of 180 degrees. You can, and it will have the contribution which is imaginary, and that's a property of the odd function, as we have seen earlier. If you have the delta functions which are real and opposite in sign, it will lead to a pattern which is imaginary and a sinusoid. Imaginary part contribution, it's still realizable. Okay, I lost. Okay. So while we go along appreciating these pairs, which will come very handy when we go on discussing things, one of the important aspect that we need to appreciate, as I said, the combination of these two variables in describing the functions in two domains appear in combination in the Fourier description. And so you will find that so is the typical spreads of functions. So if a function is wide in one domain, you will find it has a narrower description or more compact description in the other domain. And that can be seen from the inverse widths that we saw of the Gaussians. We will also relate that to the uncertainty principle. So this is the, you can also relate them in stages where you can identify pairs associated with the uncertainty principle, Heisenberg's uncertainty principle, where momentum and position coordinates can be identified, and you can see that this is a statement no different from the limit of spreads. The spreads can be wider in the case of not so well-defined functions, particularly when there is randomness. You might have widths in the other domain which are wider than the inverse of the width in one domain, and so on and so forth. But they cannot be narrower than widths of inverse of widths in another domain. For example, if width here is delta t, then the other width cannot be narrower than 1 upon delta t. Okay, I will skip over these other details. I don't know how much time I have. Do you have some idea of the time?
Yeah, I think we are running short of time.
Okay.
Yeah.
So we will, this might be a good place to stop
yes.
and take questions. Okay.
Yeah, there are some questions for you in the chat window.
Okay, all right.
Debashish, he said, heard you earlier, and yeah, he writes here.
Okay, I'm just trying to get to the chat window, not.
Hello, this sir, I am Debashish from Assam. Attended one of your summer school talks few years ago at Cotton University, Guwahati. Nice to listen to you again today. I have two questions. How Fourier transform handles spurious harmonics? Do they get slipped through the gaps left behind by the linear approximation?
How Fourier transform handles spurious harmonics? They are you referring to things that the harmonics that might be generated in the process of computing Fourier transforms using some non-ideal process, for example, some quantization or things like that?
Debashish, you can...
Oh, you can probably unmute yourself if that is allowed.
So it is the inherent harmonics which are generated in the system, like while analyzing some light curves of some variable stars, somehow we encounter some harmonics, and how to handle this type of things.
Yeah, but the harmonics might be a valid, pretty correct descriptor of the light curve details. For example, a pulsar signal, okay, which is a repetitive signal with nice looking pulse profile, which repeats. If we were to describe that in the Fourier domain, we will require a large number of harmonics of the pulsar frequency and appropriate amplitudes and phases of it, and to properly capture all the details with high fidelity, in fact. So I'm not able to relate the word spurious to the description. Suppose you have a function and you take its Fourier transform. If you've done it correctly, and have the data represented with proper fineness in the description of the amplitudes and so on, then you will the process would not have produced any spurious results in your Fourier description, including the harmonics. So could you elaborate on the word spurious?
Sir, suppose in studying the seismology, and we sometimes encounter some spurious signals in the light curves, and while doing simple Fourier transformation,
Yes.
does those information get lost in the process of transformation?
No. See, yeah. So one of the things to stress is Fourier transform, as long as you do not have any huge quantization and certain other limitations of representation of the data with limited number of bits or things like that, you would get the Fourier description, which is authentic representation of the whatever input description that you give. The input description itself might be might have some non-idealities produced because of response of the system through which those outputs are obtained, which you have recorded. If they happen to be, for example, have some level of non-linearity, okay, if the signal that you recorded is produced through a slightly non-linear system, then you would find that if a sinusoid was input to such a system, you would produce some harmonic content at the output when it was not there at the input. But having presented this to a Fourier analyzer, you would not need to worry about the Fourier transform itself producing some spurious results, unless you have suffered through some quantization in representation of the signal that you presented for Fourier transform.
Okay, sir.
He has another question here. Which transformation technique is best for analysis of non-stationary data?
Non-stationary data, there are a variety of aspects associated with non-stationary data. You will find that the Fourier domain description will actually handle that pretty well. It will, of course, have to be viewed over appropriate scales. For example, many of the aspects of changing statistics and so on, or properties of the signal as you go along in time can be captured by Fourier transforms, or by things where short Fourier transforms are looked at, and stacks of such Fourier transforms, what we call a dynamic spectral description, can be used, or people use wavelet transforms and so on to capture the details where the signals might exist for only a short time, and so on and so forth. So there are a variety of techniques. Fourier transforms are not entirely inadequate to handle the non-stationary data.
Okay, sir. Thank you.
But if you take long transforms, stretches, then of course you would get more combined description of it, and you might lose the detail of how things are changing as a function of time. But there are ways to overcome that by looking at finely viewed in time the spectral descriptions and viewing them how they evolve as a function of time. And this is how many of these phenomena are studied in detail, including the fast varying phenomena. Yeah.
Okay, thanks, Desh.
Okay. Yeah, I must be delaying the next presentation, so I will probably stop.
Desh will be with us for the next 2 days as well. So same time, you can get back to him with doubts tomorrow. Thanks a lot, Desh.
Okay, thank you.
Yeah. So with this, we come to the next talk.
Yeah.
Okay, I will stop sharing.
Thank you.
Yeah, thanks.
Thanks a lot. See you tomorrow.
Okay, is there the talk following me is which one? I have not noticed
This
it.
is Timothy Hamilton.
Okay, I will probably stay back.
Yeah, he's doing AGN spectra.
Okay, all right.
So, yeah, you're most welcome to stay on.
Okay, yeah, I will see how,
Yeah.
He's already-
So you may not see me going away immediately.
No
I think
problem.
you
You
should-
stay. You're most welcome.
All right. But
Yeah.
you can take away my permissions as a host.
That's okay.
No,
Not a
that's fine.
problem.
No, so that I don't end up pressing on some button.
Okay. Yeah. So Tim, welcome. Sorry for the delay. Hello.
Oh, there we go. I had to unmute myself there.
Yeah.
Hi, that's fine.
Yeah.
Good evening, everybody. And
Yeah.
let me get my video on here.
Just a minute. Let me just welcome you.